Alright, for this external convection problem, I've chosen 7.19. Steel plates of thickness 6 millimeters and length of 1 millimeter on one side are conveyed from a heat treatment process and concurrently cooled by atmospheric air of velocity 10 meters a second and temperature ambient of 20 degrees Celsius and parallel flow over the plates. So for an initial plate temperature of 300 degrees Celsius, what is the rate of heat transfer from the plate? And what is the corresponding rate of change of plate temperature? The velocity of the air is much larger than that of the plate. So, writing down some important givens, just some geometric qualities of the plate itself, air and temperatures, and then some of the parameters of the steel itself. So we can assume constant flux. This is a steady state and constant properties. So starting out with the analysis, to find our rate of heat transfer, we're going to go ahead and shoot for this equation. Q is equal to 2 times the convection coefficient, length squared, so the area over it, and equal to our difference in temperature. So in order to have this, we need to find our convection coefficient. So we're going to go ahead and use the Nusselt number to do that. Before we can get started on that, we need to find a Reynolds number in order to determine the equation we're going to use for that. So Reynolds number, we have the velocity times the length over our dynamic viscosity, or so what we're going to do is plug those in, and we get a value of 3.3 e to the 5, which is less than the 50,000 we need for it to be turbulent. So that is the critical value. So we have laminar. So now that we know it's laminar, we can say constant flux, and laminar, we can go ahead and use this equation for Nusselt number here. So plugging the Reynolds number, the Prandtl number, I believe, which is given from a table, and then just some of the constants, we can get this number here, 346, which we can go ahead and use up here to find our convection coefficient. So plugging in the K for steel, our Nusselt number we found, and the length, we can go ahead and get 12.486 watts per meter squared Kelvin. And then we can go ahead and plug that into that equation we set out to use initially, and we'll get 6,992 watts. So then to solve the second part of the problem, we're going to go ahead and do an energy balance around the surface. So we have our energy out equal to the energy stored. So solving for that, we have the rho times delta times length squared times our Cp times dt over delta temperature over delta time at this position I, which we are going to go ahead and solve for that dt, which just ends up being that heat transfer over the rest of those terms. So which we have, as they are all givens of either from the problem or just from 1010 steel in the table in the book. So we'll use those, plug those in, and we get negative 0.271 degrees Celsius per second. And that's the problem.